Okay, we're going to examine an Egyptian problem solved by the method of false. The problem is solved by the method of false position. A quantity and it's 1/7 added together become 19. What is the quantity? And so if we were to do this by modern mathematics, we would simply assign the quantity x, and you add together 1/7 its quantity, which would be 1/7 x, and you would arrive at 19. You would simplify 8/7 x equals 19, and you would multiply by the reciprocal to get x. And you would get x is equal to 19 times 7 over 8, and if you want to simplify it, it would be 133 over 8. That's how we would arrive at our answer through modern methods. But we're looking at it through Egyptian methods. And so the Egyptians use something called false position, which is where they come up with a random, not a random guess, but an intellectual guess that will simplify the math. So you're looking at a quantity, and you're going to add 1/7 of it together. So an obvious place to start is 7, because you're looking, if you create 7, then you know you're going to get an integer for the 1/7 as well. So if we assign, there's no x in the Egyptian math. We'll just their variable is going to be just a number that they choose by false position. So we're going to start with 7. A quantity and its 1/7 are added together. So its 1/7 would be 1 is equal to 19. Now you would get 7 plus 1, and you get 8. Now 8 doesn't equal 19, but 8 is 8/19 of 19. So if you multiply 19 over 8 by both sides, if you multiply this side by 19/8, you'll get 19. So now we go back to the original quantity, which is 7, and we multiply 7 by 19/8, thus arriving at the same solution that we got through modern methods of 133 over 8. Additionally, well, first of all, we should talk about false position. It's inefficient because you have to choose an integer value first, and then you get to a random number, and you basically have to multiply to get to the number that you want, and then go back and do it all again for the very start of the first quantity that you chose by false position. It's not a proof-based method. It's not really a foolproof way that you'll get the number every time. It's false position because it's false, and you're making a guess, an educated guess, and then you have to get to the number. And one more thing that the Egyptians do that is really silly is they don't use mixed fractions unless they only use mixed fractions, and every fraction has to be 1 over an integer, and they don't have these top-heavy fractions like this. So then after this, you have to simplify 133 over 8. So first you do 8, you double that, 16, you double that again, 32, you double that again, 64, and you double that again, 128. Now, since we've doubled enough that we've gotten to a number, well, we can do one more and do 256. Now we know 133 is in between these two numbers, so we're going to take numbers here that add up to 133. Now in this particular case, 128 is the closest you're going to get to 133 with a remainder. So it's 16, and then you have remainder 5 left over, so it's 5 over 8. 16 and 5/8 isn't their full answer though, because Egyptians don't use 5/8 as a fraction. It has to be 1 over something plus 1. It's fractions added up, and the only fractions that they have are 1 over an integer. So right here you have 5/8. 5/8 would break up into 1/2, which is 4/8. Well, first it would break up into 4/8 plus 1/8. Right, that's 5/8. And then 4/8 is 1/2. And 1/2 plus 1/8 satisfies the way they do math. So the answer to this problem would be 16 and 1/2 plus 1/8. And that's the solution. But as you can see, the Egyptian method did work, and it did get us the same way as the modern method, but it took much longer. Even this part alone isn't quite as intuitive as up here in modern methods. Assigning a simple variable x makes it much easier. You just cancel out the coefficient of the variable, Down here, you have to do the false position. You don't even get the right number, and then you have to do this multiplier and readjust everything. And then once you get here, which already took longer, then you have to convert it into the way that they describe fractions, which is, they did it their own way. We're not sure why they write it this way, but this is why they do it. And yep, that's the answer. This is the solution to an Egyptian problem. This is project 1.